Hello everyone, welcome to our class of electrical energy conversion system. So today we are gonna just make an introduction to this course, how we will make this class this semester, spring 2025. What do you need to know in this class? What are the objectives? What is the syllabus? And how we will conduct this class during this semester. So firstly, I'd like to introduce myself. I'm Abu Bakr Salem. I'm assistant professor, previous assistant professor in West Virginia University, and I'm currently working as a lead engineer in industry. So let's start together discussing about the basics of uh, conventional electrical power network, and this is going to be an introduction to our course to understand what is the benefits of learning electromechanical energy conversion or electrical machines. So let's start, guys, with this conventional grid. So like mobile phone, guys, we have old or conventional mobile phones, and we have also smart mobile phones. So you can see the very old telephone and the most recent iPhone, for instance. There is a big difference between these type of phones. For sure, conventional systems are very traditional, has very some limitations to adapt our new life, and the same is for the conventional electrical grid as well. So let's firstly discuss and see what are the elements we have in our conventional electrical power system grid. So firstly, this diagram, guys, shows a complete electrical power system grid. Grid means the electrical network. So we classify the network, guys, into three main parameters. What are these parameters or these stages? We have generation stage, we have transmission stage, and we have distribution stage. Generation stage means the stage that we generate electricity. For sure, in order to generate electricity, we have some electromechanical conversion systems, or sometimes converting some other forms of energy to electrical energy, like, for instance, getting power or electrical power from photovoltaics. So this converts light into electrical energy. So it's not only electromechanical devices. So we can convert different forms of energy to electrical energy and have it as an energy source. But the traditional, or let's say all traditional electrical sources in generation are electromechanical. Electromechanical means we convert mechanical power into electrical power. And for sure, mechanical power should have some systems, some mechanical devices to generate mechanical power firstly, and then converting this mechanical power into electrical power. So this is called generation stage. So this is the first part here on the left-hand side. Within the generation stage, guys, we generate electricity with a certain voltage level, let's say 10 kilovolt, 15 kilovolt, 12 kilovolt. So this is the range of voltage generation. So the generator itself will provide a supply of 10 kilovolt. You know, guys, in electrical circuit, we describe electricity by means of volt. So volt is the voltage level that we connect our circuits, and we absorb from these power supplies, we absorb current. And if you multiply current times volt, this is nothing but power. and power versus power in a certain interval of time. So this is going to be energy. And we will describe more about power, voltage, energy, and different types of AC power in our introduction in our course. So let's continue in our discussion here for the conventional grid system. So we generate the electricity at, for instance, 10 kilovolts. Now, our loads at homes, I'm sure you 100% know that our electricity at home single phase supply is 110 or 115 volt. So it's very low volt compared to that 10K. So we have a classification for the voltage levels. So less than 1 kilovolt, guys, is called low volt. Between 1 kilovolt to 6 kilovolt, or sometimes higher in different standards, sometimes up to 10 kilovolt, for instance, it could be medium volt. Sometimes to 15 kilovolt, also it's called medium volt. So here in the United States, we consider the 13 kilovolt, the 15 kilovolt as medium volt. So we have also, guys, what's called high volt. So 66 kilovolt is high volt. 138 kilovolt is high volt. 230, 345, 500, 765, all of these voltage levels are called high volt. In some other standards, they call it extra high volt. So it depends, guys, on the definition. Okay, but we can say by the end we have low volt, we have medium volt, and high volt. So we generate the electricity in electrical power generation station by such voltage levels, which is called medium volt. Now, in order to transmit this supply to our loads, so this is the generation stage, and here is our customers. So by the end, we will provide the supply to our customers. So by the end, we have here some loads. So loads are nothing but our customers of customers who use our electricity that we generate. So most of customers, if we see the domestic loads, as we mentioned, we have at homes, for instance, we have 115 volt. Or if it is line to line, it's 220 or 240 volt. So this is called line to line volt. So how can we transmit our power to customers who needs supply volt of 140 of 110 or 115 or 240 or 220 volt line to line from the 10K? We found that if we start transmitting the power at this voltage level, guys, we will have huge power loss during transmission. We will have some numerical examples on this point, why we use transformer, because transformer is going to be one of the topics in our class. So we use transformer mainly to step up the volt in the beginning after generation, and then stepping down the volt again before starting in distribution. Why? This to reduce the losses during transmission, because we generate power in certain voltage level, but by the end the power is going to be in volt ampere. You know that power or apparent power is measured by volt ampere. So let's say 10 kilovolt and, for instance, 4 kiloampere. So if you multiply these two values, so it would be 40 megavolt ampere. So we have here 40 megavolt ampere, for instance. So if you start transmitting this 40 megavolt ampere without using transformer, you may end up that this 40 megavolt ampere will be dissipated during transmission and will not reach to our customers. So in order to do that, guys, we start firstly using a transformer. This transformer is going to step up the volt, and stepping up means when you step up the volt, so step up transformer means step up the volt. But this is for volt. What happened to the current? Since if we assume that we have ideal transformer, which means we don't have any losses within this transformer, so the input power and output power should be the same. So you have 40 megavolt ampere. Assume that the volt is here 10K and you make the volt 100K in the secondary side of the transformer. So you multiply the volt times 10. So the Turner's ratio or the factor that we use to step up the volt is 10. In this case, if we assume that the transformer is lossless, so we would have also reduction or stepping down for the current by 10. So we have 4 kilo ampere. So on the secondary side, we would have 4 divided 10, which means 0.4 or 400 ampere. So once we reduce the ampere from 4K to 0.4K, you know that any power loss means I square times R. R is nothing but the resistance of the transmission line, the cables that we use to transfer the power. And I square is the square of our line current. So since you already stepped down the current, so the value of I square R would be less. This is one factor. Another factor is if you need to transmit very high currents compared to low current, so this means the cross-section area of the cable or the transmission line would be smaller. And if you have a smaller cross-section transmission line, this means the cost of the transmission line or the cable would be less. For sure, if you would like to have like 10 gauge wire compared to very huge cross-section wire of cable, so the 10 gauge wire is much less in price. So this is why, guys, we step up the volt after generation. So after generating the volt and using transformer to step up, this stage here is made in the generation station. We start in the transmission station. So we have the second stage, which is transmission. And the transmission, as you can see here, guys, we have many voltage levels. And after the transmission, we have what's called substation. And the substation is used to step down the voltage again. We don't step down the volt, guys, to the same voltage level of domestic loads, which is 110 or 220 line to line. We made it in levels as well because you have some customers need relatively high voltage levels. So for instance, if you have a factory and this factory needs high power, very high power, it's not making sense to give or deliver the power to this customer in 240 volt. It has to be very high. It has to be very high in order to support his amount of power. So, for instance, we may have some customers need 13 kilovolts. We may have some customers needs more. So up to the customer requirements, guys. So we would have different voltage levels now on the substation according to the requirements of our customers. For instance, we may have, as you can see here, sub-transmission system. So we'll provide the volt in 26 and 69 kilovolt, and this customer will be responsible of stepping down the volt and start supplying his customers, for instance, okay, or his loads. So we call it sub-transmission because he still need to make some more transmission for this volt or this network. And we may have primary customer like a factory, for instance. This factory needs 13 kilovolt, needs 4 kilovolt, okay? And you may have domestic loads, which needs just 120 volt line to neutral or single phase or 240 volt line to line. So you know that in our homes, you may have some circuits require 120 volt, like the regular sockets, the regular lights at homes, small devices. But if you see the air conditions, big or high power, relatively high power devices that could be more than 10 kVA, for instance. So we do prefer to supply these loads by line to line, which is 240 volt. Okay. So this is going to be the last customer or the least volt we have in our network. So this is, guys, called conventional grid. So again, the conventional electrical power network consists of generation, transmission, and distribution. Generation to generate the power at medium voltage level, then tipping up the volt to be transmitted. Then transmission has many voltage levels, as we can see here: 138, 230, 345, 500, or 765 kilovolt. And after that, tipping down the volt in substations to be distributed to the different customers. So this is the distribution network. So all green part here, guys, is the distribution part. All black parts are the refer to the parts of generation stage, and the blue parts here are the transmission network. If you have a look to this grid, guys, we don't have a source of power at the customer sites. So what happens if one customer here, for instance, has some photovoltaic, rooftop photovoltaic system? Can he start generating the power to this grid? So we would have some problems now. Problems in stability, problems in power flow, problems in protection. So a lot of problems we would have if you have some sources at the load side. For that, guys, we call this conventional grid as centralized power generation, because the power generation is only centralized in the generation stages. But if you have some electrical sources in the customer side, so we call it distribution or distributed resources. Distributed resources like what? Like photovoltaic. Like, for instance, if you have electric vehicle and you connect this vehicle to grid, so it would provide some energy to grid if the car is not charging. So we call it vehicle to grid, V2G. You can hear about that in research work now in electric vehicles, something called V2G. Okay, V2G. So V2G means transmitting power from vehicle to grid. So the electrical vehicle itself, it has some batteries. So these batteries can start generating power and deliver this power to grid. So it supports the electrical grid. So how can we have all of that in our traditional grid? It's not easy. We should have some modifications in our network in order to allow connecting such new devices. So let's see, guys, another definition for the electrical grid called smart grid. As we mentioned in the beginning, guys, as we have conventional or traditional phones, we have also smartphones. So what is the meaning of smart grid, guys? So smart grid can have a lot of the following systems, like, for instance, renewable energy sources. So you can use, for instance, wind energy. So this is a section for the nozzle of a wind turbine, includes some devices here inside. And as you can see here, this is 3 megawatt onshore wind turbine platform. So for the wind turbine, guys, we have what's called onshore and offshore. So onshore, this is on the sea level, on the sea shores, but offshore means it's far from the water sources or sea. Okay, so this is called offshore. So we have these two types of wind energy systems. We have also electrical vehicles and powertrain. So electrical vehicles, as you can see here, this is electrical vehicle, and powertrain, you can have powertrain also that can be connected. You can have ships, big ships. You can have aircrafts. So all of that, guys, are some like sources of electrical machines, some types of electrical machines. And these electrical machines, by a way to or another, can be connected now to our smart grid. So our grid has to be different to support this type of machines. So electric vehicle, it has batteries, and these batteries need to be charged. So we should have charging stations. And these charging stations should provide power to the electric vehicle, and at the same time, you should have like charging station at your home or small charger at your home that can charge your vehicle, or at the same time it can support the grid. So the grid has to be smart to allow the energy to be bidirectional power flow. So instead of have only, let's see that in our previous slide. So here, instead of have only power flow is moving in this direction all of the time, no, we need to have the flow of the power in the other direction, or between the different loads here, not only from the source to the supply. So this is called bidirectional power flow. So, or energy flow. So this can be applied in smart grid. So these sources, these types of loads, guys, are requiring smart grids. And actually, these type of loads have a lot of types of electrical machines or electromechanical energy systems or conversion systems. So in order to understand more, guys, let's see this diagram here. So this diagram is for an electrical drive system. Let's say, for instance, we have one system of the previous systems we could see in the previous slide, like for instance, vehicle, like part of this wind turbine, like part of the air crafts, like part of powertrain, okay, like part of solar power tower. So this is called solar power tower to generate electricity by means of sunlight. So let's see one example of a drive system. So what is a drive system? Drive system actually, guys, includes some devices like what? Like a motor. And this motor will be connected to a certain load. If we, for instance, say our, let's have example as one of our loads at home, like our ceiling fan, for instance. So the ceiling fan has internal motor, and the load is nothing but the blades connected to the motor. So this is the fan blades. This can be considered our load. And when these blades are start rotating, it will make friction with air. So the air friction and the blades rotation both will be loads on our motor. In order to control the motion of our motor, guys, like for instance, we need to have a certain speed for our fan. You know that in your fan, you can have like selector switch to change the motor speed or select the fan speed. So how this motor change the speed? Simply we have what's called a feedback, a sensor to measure the speed and control this speed to a certain command or reference value. and calculating the error. So the error is nothing but the difference between the setting value, this is the setting value, or the command, and the measured value we have from the real operating system. The difference here is nothing but the error. So I can draw small block diagram like that. So we have our plant or our motor. Here, the motor has a certain output. So this is our motor. And we will have another block here. Later on, we'll discuss it. So this motor has output, which is the motor speed, for instance. So we sense the motor speed and then return this back and compare it with our reference speed. So this is the speed reference signal or command. This is in plus sign, this is in minus sign. The difference will be the error. So the error will be applied here, guys, to a controller or a control system. So this control system, along with a device called power conditioner or power processing, will do the modification on the main supply, which is, for instance, regular AC supply, 120 volt, in order to provide the controlled volt to our motor to achieve our load requirements or load speed. So this is called, guys, drive system. And this drive system, as you can see here, we have one part which is motor. The feedback, we will have some sensors. The control unit could be any microprocessor. The power processing or modulating unit is a power electronics unit. And this is a complete drive system. So if you would like to see, guys, where will you see the parts of this system in your courses, for instance? So motors, we will see motors in our class, which is EE 335. Loads, any types of loads, mechanical loads, for instance, and we will discuss a bit about these loads because we don't have electrical drive course in our school. But one of the advanced courses is called electrical drive. We will have just few flavors of electrical drives in our course because it's a complete separate course called electrical drive. The feedback is through some sensors. So you should learn about sensors in the instrumentation lab. And PLC lab, you will learn something about the sensors. So sensors will measure the non-electrical signal and convert it to electrical signal and convert that or interface that to a controller. So the controller could be, in our life, could be PLC, could be microcontroller. So PLC, you will learn that in instrumentation lab as well. Microcontroller, this is 320 EE or CPE 320 or 321. I don't remember the code of the course, but we have this course in our school. And I believe most probably all of you guys already learned this course. Okay. And what happened inside here? So this is nothing but the microcontroller, but inside here you will have some control algorithms. So the control algorithm, you will learn that in a course called control. And some of the parts of the control you will learn in signals and systems as well. Okay. So you will learn these courses with Dr. Litchfield and Dr. Davari. And this is a power electronics. I was teaching this course before, EE 435. Dr. Hatiboglu also is teaching this course. So this is called EE 435. So you will learn some of the power conditioner circuits. So the power conditioner or power modulating or power electronics circuits will convert AC power or uncontrolled AC power to controlled AC power. Here in this example, it could be from AC to DC or AC to controlled AC or DC to AC or AC to DC. So any form of power conversion, sorry, not power conversion, I mean electrical power conversion from form to another form. This is nothing but power electronic converter. So this is the tasks you will learn in this course. It's an elective course, and this is very important course, by the way, guys. So I guarantee that more than 60% of the job vacancies in the market are in power electronics and control. So this is very important topic, and I recommend you guys to take this class. This is very important class, and especially for our new smart grid. So for a smart grid, guys, you need to have a lot of power electronic converters in the grid itself in order to allow the bidirectional power flow and control flow. Okay, so this is now, guys, a complete example for an electrical drive system. One of the parts we have here, guys, is the motor. And in the previous or few slides ago here, we have also transformer. So motors or transformer, we will learn that in our class. So this is a classification, guys, for electrical machines. So we will learn some of these machines. We cannot learn all types of machines for sure. If you'd like to learn all types of machines, you will need at least 3 courses in order to cover the different types of machines. But we will focus on the most important machines that you will need in industry, and at the same time, the machines that you can learn for undergraduate level, because there are some other machines you cannot or it's not that easy to learn that in the undergrad level. It should be in postgraduate level during master or PhD degrees. Also, for any type of machine, guys, we will learn the student version model, because if you would like to have the exact model, again, this is not undergrad level. This is a relatively higher level, and to be honest with you, you don't need it to work in the market or industry. But if you are going to work in R&D, research and development, 100% you will need more detailed or more advanced courses. Okay, so what are the types of electrical machines? The books classify electrical machines in different ways. This is one of the well-known classification. So we have, for instance, AC machines, DC machines, and special machines. So these types or this classification is based on the supply. So according to the supply type, the supply could be AC. AC means pure AC supply, single phase or 3-phase, sinusoidal supply. So on, so single or 3-phase supply. We have DC machines. So DC machines are supplied by DC source. It could be pure DC, it could be rectified DC. Or special machines. Special machines means it needs special types of supply. Like for instance, some pulses. Or the machine itself has special type of connection. So this is called special machines. For the AC machines, guys, we have synchronous machines, we have induction machine, we have transformers. We will learn synchronous machine. So synchronous machine, you can find synchronous generators in most of power plants, and you can find synchronous motor in some applications, like for instance, in some electric vehicles, or you can find synchronous generator as well. Some types of permanent magnet synchronous generator in wind turbines and renewable energy resources. So this is for the synchronous machine, and we will learn one complete topic on the synchronous machine, and we will focus on the generator because the majority of our loads our use of synchronous machine in industry, especially in power plants, is for synchronous generator. Also, we have induction machine. So induction machine, guys, we call it the black horse of motors. For the time being, guys, we can say that more than 60% of motors we use in industry are induction machines. So we will learn three-phase induction machine in our class. It's mainly used in industry in motors, but still we have some induction machines used as generator. This can be in wind turbine. So wind turbine, we have 5 different types of wind turbine systems. 3 of these types are based on induction generators. Some is called self-excited induction generator, and some others are called doubly fed induction generator. So these types are used in wind energy. But to be honest with you, this topic is not easy to be covered for undergrad level, and also we don't have time to discuss the induction generators in our class. So we will focus on the induction motor in our class. So we will learn also this one in our class. Transformers, as we discussed, guys, transformers are very important for power transmission. So after generation, we need transformers to step up the volt, and before of distribution, so we have in the substations we have transformers. So we will learn also the transformers in our class. The other type of machines, guys, is DC machines. We will learn also some of the DC motors. We will not elaborate in DC generators because it's obsolete. It's not exist anymore in any new systems. You can find this very like rarely in very old devices, but most probably will not see that anymore. So DC generators are not used anymore. So we will focus on the DC motors and what are the applications we have in industry that prefer using DC motors. Special machines, guys, like stepper motor. So stepper motor is mainly used for the applications that require holding torque, like printers, like watches. So this is one of the very well-known machines. Also, you can find this in small cars used for control. You can find this also in drones. So this is one interesting type of machines, but we don't have time in our class to cover this topic. But you need to know that one of the motors is called a stepper motor. Also, there is one type called universal motor. So universal motor is a DC motor but supplied with AC supply by connecting the windings in series. So it's special type of connection, and you can find universal motors in fridges. So fridges are using universal motor. Switch reluctance motors, guys, you can find this type of switch reluctance motors in elevators. You can find it in some of electric vehicles. So switch reluctance also is very well-known type of special machines. But again, we cannot cover this type of machines in our class due to the time limitation. Here we have some subcategories for every machine. For instance, the synchronous machine, it could be permanent magnet synchronous machine. It could be PLDC or brushless DC machine. So brushless DC, it doesn't mean it's DC machine. So brushless DC, we call it PLDC because it's supplied by DC, and then the DC will be converted to AC by means of power electronic converter. but the machine itself is still one of the synchronous machines types. So it's called BLDC machine. So you will find it a lot also in applications. Okay, but our discussion in the class will be on the field-based synchronous machines. Okay. Also, we have synchronous reluctance machine, but our machine that we will discuss is the field-based synchronous machine. But there are some other categories you can find some of them in industry as well. For the DC machine, guys, we have separately excited DC machine, we have series DC machine, we have shunt DC machine, and compound DC machine. We will focus on the separately excited machine, which is more or less the same characteristic like shunt machines. So this is what we will cover in our class. In our course, guys, so these are the topics that will be covered. So in our course, guys, firstly, we will use this textbook. This textbook is very interesting one and very easy. If you would like to have the book with you, this will be very good as a reference with you in all of your life, not only during our class. So this is a good reference. Even I'm still using this until now in my life, not only for teaching your class, but sometimes I need to return back and see something or read something from this book. So this is very nice one. So I do recommend, guys, to have this book with you. However, if you didn't get this book, all the course materials will be shared with you on slides and eCampus. So you don't need to have external sources to read or to succeed in this class. So I will share with you all required materials. In this course, guys, we will cover the following topics: the power transformer, the DC motor types, and we will elaborate more in the motor starting, speed control, and drive circuits. For the synchronous machine, we will discuss the machine as generator, as motor, and also we will elaborate more in the different types of rotating and linear types and discuss the dynamics of synchronous machine and synchronous machine control. Also for the induction machine, guys, we'll discuss a bit the idea of having induction generator and more discussion in motor and different types, single or three-phase. And we will focus more on three-phase machines. We will not discuss a lot in single-phase machines, but we still have single-phase induction motor used in our life, like for instance, what we have for ceiling fans in homes. So this single-phase induction motor. But the most important is for the three-phase machine, how to start the machine, how to make speed control, and what are the drive circuits used for these machines. By the end of our course, we will elaborate more, guys, in the variable speed drives. I mentioned to you that we don't have electrical drive course, but this course is this topic is very important because in industry you cannot have a motor operation without drive. So we will discuss more about the variable speed drives, or we call it variable frequency drive sometime, VFD or VSD. Okay, so we will discuss the induction drive and DC drive, which means variable frequency drives for induction motor or for DC motor. So these are our course topics that will be covered. I'm expecting from you guys to learn in this course. So this is the course outcomes. So to apply 2-watt meter method. So what is the 2-watt meter method? We will discuss this in our first topic, which is related to power measurements. Identify magnetic material and magnetic circuits. So we will discuss something about the magnetic. We didn't discuss it in the topic, but this is introduction to transformer. So in the transformer part, or before of transformer part, we will discuss firstly some topics in magnetic circuits. Then you would understand also the principle of operation and construction of DC motor and generator, performance analysis, voltage speed control. So you should learn all of that by the end of the course. Also, you should be able to identify the principle of operation and construction of network models of various transformers. In addition, you will be able to explain the performance analysis of motor operation, starting, speed control, the circuit of motor, the applications of motors for the three-phase induction one. Also, to be able to analyze the performance and regulation of synchronous alternator or generator. So alternator means generator. You should be familiar with the infinite bus. So what is the infinite bus? We'll discuss that in our classes. The active and the reactive power control and applications. Also, you would be able to explain the principle of operation and characteristic of three-phase synchronous motor. Finally, you would be able to identify the electric machinery ratings and general design consideration if you need to select or design a motor for a certain load. So these are the learning outcomes of our course. Again, this is detailed topics of our course, guys. So I made it here in numbers. So the basic of electromagnetic and electromechanical energy conversion system. So this would be a first topic. And the first topic is after the revision of AC power. Or we can, guys, switch between the topics during our classes. So I would start with the three-phase power before the magnetic, but these are the course topics. Three-phase power measurement and power factor correction. So this is the second topic, but I'm going to start with this one in the next class. Then power transformers, DC machines, AC machine fundamentals, synchronous generators, synchronous motors, induction motors, and by the end of the course, I added variable frequency drive as an option. If you would like, guys, by the end of the classes to know more about the special machines, if we have time, we can also discuss this by the end of the class. Another way to know more about the special machines, we can have a 101 session together, and it could be a course project. Every student or some groups, we can make some groups in our class, and every group can make a report and presentation on one of the special machines and discuss this type of machine to all of the class. So this would be in one session. So this can be a good idea also to cover this part of special machines in our class. This is the grading policy, guys. So for the homework and assignments, it contributes by 40% of your grades. The homeworks, guys, is gonna be non-grading homework, which means once you submit the homework within the time frame, you will get the grades. But you have to submit the homework complete. But please follow up the eCampus. You will have the announcement on eCampus. If you submit the homework late, for sure you will have deduction. For the midterm exams, we will have 2 midterm exams. Everyone is 15%. So total midterm is 30%. And the final exam is 30%. And for the general rules, guys, of the grading. So it's standard grading as per the university. So you know that 90 above 90 is A, 80 to 90 is B, 70 to 80 is C, 60 to 70 is D, and under 60 is F. So this is the grading policy we have in our class, guys. So we finish our material today. We will meet in the next class. So as I shared with you guys, the syllabus on eCampus, expect to have the class recording and material every Tuesday and Friday at 8 p.m. So this is the time of the class. And if you have any question, you have the office hour announced on eCampus. So please, you can send me an email to meet you on Zoom, or if the office hours are not convenient for you, so please send me an email. We can assign a time meeting and we can meet together to discuss any challenging. The time of the midterms will be announced during the semester. Most probably the first midterm would be in week 7 or 8, and the second midterm would be after week 12. So this is the plan to our class, but we can discuss more about that, guys, in our synchronous meetings of our lab. By the way, the lab sessions, we will start the lab sessions in week number 3. So we don't have labs for week 1 or 2, because for sure we need some time to cover some materials in our class and start in our lab. And we will discuss what you need exactly in your lab. Thank you so much, guys, and see you in another session.